So I'm going to talk about polynomials. These are very important things in terms of mathematics. It was studied by lots of French scientists worldwide. Um, Basically, what will happen is that you'll have um, a sum of different things in few spaces. The first writing that is used to describe polynomials is this one. Basically, you will have a coefficient, a thing to multiply, an unknown thingy that you usually call x to an exponent. But basically, what will happen is that it will form a space as a linear combination of each of this thingy, so that you can actually have very specific things in terms of topology. Very fast, the mathematician figured out that you could rewrite this as being a product. Where is it? Where's my script? Script. Large operator. This. You can rewrite it as being sum of the alpha I x to the power k to the power I. Oh, no, not like this. Not like this. Okay, to be x minus alpha to the, yeah, this. Okay, where I is in the system sigma. So very quickly, it has been figured out that the polynomial was actually being zero at some places, and that depended on the order of the n, the order of the polynomial. And very quickly this appeared. This thingy was basically saying that you could count that the polynomial could be zero, and when you figured out this, you can have another expression, which is this one. But there was a problem, because actually couldn't imagine doing this transform, like going from here to here for all numbers, because there was something, the complex number weren't invented yet, so you couldn't like think of a way to transform it, even though now we have very fast way to do that. You couldn't like think of it, while the transform from this to this was just developing. Like you have something, a multiplication, you just put it like trivially from this form to this form. So then there was the invention of, well, not the invention, but the concept of complex number with another space on itself was invented. And actually the fact that the other plane, another another whole space, like there is 1D, and then you add another dimension to this, just because the root has to be on another thingy. Like you can't put it in reals, because if you add it on reals, it doesn't just fit the equation. So obviously I could talk about the one and two, or one first and second order equations, but I'm not going to talk about it because it's boring. So I'm going to talk about infinite dimensions. So what will happen is, very quickly we figured out that you could also rewrite as a third form. Well, there is fourth one, but okay. You could rewrite this as being the a as being, wait, I'm not going to use this one, as being where is it, this one, a b c, and say that it equals to the same triplet being 0 and 0 and 0, but this was actually when you multiply it by a power of x. So you had that's exactly why matrices were invented, just to solve these polynomial problems. Like they had few laws that were discovered earlier. There were a few, well, actually, for the matrix thingy of polynomial, it happened more with English mathematicians, which is kind of sad. Um, because of the kernel and things like that. So yeah, they had the system like this where you could rewrite it like that. But then someone had the idea, what if you have multiple unknowns? And that was like, what? What? You can have multiple unknowns in your system? What to do now? What to do now? You had to rethink of it. So the English ones were like, what the fuck? What the fuck? I need to redo something. So they took a matrix, they put the A, I'm taking a 3 by 3 just as an example, A, B, C, D, E, F, G, H, Y, which were the known coefficient of each of the equation. Well, not like this, thanks. Times the other matricial product being the same thing, being, well, where is it? Where is it? Ooh, this one. Being x1, x2, x3, being the triplet 0, 0, 0. And now, with the formalism of the matrices, plus the knowledge of complex thingy, you could applicate something that was just two-dimension to way more vast thingy. And then there were actually very, very powerful thingy that happened after with the research on matrices, things like that. So the most important things to know about this is that um, the sum of the roots equals to what in French we call the trace, the trace, the trace, which is actually that in this matrix, if you sum the diagonal terms of this, you'll end up with the sum, if you sum this, that will be called the trace, and that sum will be equal to the sum of roots, which is actually very interesting because it means that no matter what you do as a transform to solve this, and there are lots of algorithms to solve this, Gauss-Jordan algorithm to solve this, uh, and then you can also proceed by normalization of Graham-Schmidt, but it's kind of tricky. So the sum of roots actually equals the trace of this. So meaning that if I know two of the roots, and well, for a system of, with 3 dimensions, if I know two of the roots, and if I know the matrix, I can just calculate these terms, a plus e plus I, and then you can just calculate the other roots, and that will be pretty trivial. Okay, so then there was called what something in France we call the polynomial, sorry, the polynôme associé à la matrice, which means the polynôme associated with the matrix. Sorry for bad translation. Okay, so you have what you have, okay, what you have a matrix. Okay, I'm just taking this one, and you'll build up a determinant, an application that will be a determinant that has bilinearity. That means that if you have lambda, well, if you have an application like var phi of it equals something, equals var phi, and I'm just going to copy that. So if you have you'll build phi so that it respects few thingy. For example, if you multiply by lambda times phi the whole thingy, it will distribute by bilinearity. And since it's not linearity, it's bilinearity. Well, technically it's n-linearity. So sorry for the little thingy. It will just distribute on one of the dimensions. So you can write the lambda like this, or write the lambda like this. Okay. There are a few other properties, but I'm not going to talk about it much. So you'll build the determinant. So that det, we call it det, or you can use the little things like in absolute value, things like that. So the determinant for the determinant is a number. Yeah, it's a number that reflects how the matrix on behave on nullification. That's kind of weird, but it will actually gives a lot of details in whether the matrix is inversible in French, if reversible, which means that the system can be solved like this, because you'll not end up with for a system 3 by 3. You can either have one solution or an infinite set of solutions, or no solution. Like, it's not possible. For example, if I tell you to take positive integers, and I want I want the sum to be negative, it's not possible. There is no fucking way to do that. Sorry. Yeah. So this. So we will build the determinant that represent the thingy. So if the determinant equals 0, it means that the matrix, well, I'm not going to build it like that. I'm going to build what's the polynomial associated with the matrix, which in French we call it key. It's key. Yeah, like this. Key with the little thingy with the name of the matrix. I'm going to talk it big by a bit. Then you put a variable. I'm going to talk it x, because it's a polynomial of a matrix associated with the polynomial. So it's a polynomial of a polynomial. Sorry, it's kind of complex. And that will translate how same as the determinant, since it's based on determinant. Yeah, and also you can also add thingy. It's on certain basis. So B here is the basis. You can have lots of bases. You can have basis changey. It's kind of tricky, but I'm going to say that it's the regular base, the usual base for real times n. Well, here 3, which is actually the determinant of the matrix B minus x to the I of I, well, x times the matrix identity of the n order. The identity is just a matrix with 1, 1, 1, and zeros elsewhere. So one's on its diagonal. When for the terms xii, but for others it's 0. Sorry. Then you will build this thingy that will translate the roots. I said. The roots of it. So for the matrix here, that will be translated as being the debt of. I'm just going to copy paste it because I'm a lazy ass. You have this thingy, and you just add minus x. Well, minus x, minus x. Okay. Okay, you'll end up with this. Okay, now what do I do about this? Uh, then you are going, okay, it's kind of complex, but there are actual formulas to develop it. For example, okay, I'm not going to give a property. I'm going to give a property for dimension 3, and for the special case where d and g equals 0, the formulas gives us. I'm not going to demonstrate it either. That you can rewrite this as being a minus x times the debt of matrix this and e minus x f g h and g minus x. So with this you'll very easily solve the system because you'll end up with a polynomial of order n. For example, here it's a polynomial of order 3 because it's a matrix 3 by 3. So the highest root will be of the highest power of x will be 2 because we start at 0. Don't forget it. And this is why mainly students usually start with matrix 2 by 2, so polynomial of order 1, or 3 by 3 because it actually solves the equations with x to the power 2, which is the most current when you study basic math. Yeah. Then what you will end up is, you see here, there is the a minus x. Interesting. Exactly as we said before, the product of the x minus the root. So what will happen is basically you'll have this term that can be simplified, but there will be other terms in non-diagonal thingy, like B, C, D, F, and G, and H, that will add few things to the polynomial, and that will give it more complex, because if you just have zeros, 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 and zeros, actually here you can trivially see the roots. Like even I can see it, and if I can see it, it means that it's not hard because I'm really bad. Here we can clearly see that a is a root, because to cancel out this thing you need to be either this one, or this one to be 0. So a is a solution, e is a solution, I is a solution. Wait, I? Yeah, I wrote earlier. Yeah, I wrote G earlier. Yeah, not G. It's I. Obviously, I can't let her. Sorry. then yeah. So we'll end up. Ended up with a polynomial that, for a matrix that is only diagonal, which clearly appears its polynomial form, and usually you know how to solve a second degree polynomial. So yeah, and what is interesting is that we have a polynomial of a system made with polynomials, and you can solve them. But in fact, the case where there are zeros, 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 and zeros on non-diagonal terms is very rare. oftenly you'll have monstrous thingy. Uh, you'll end up with monstrous thingies with exponential I pi my dick. Okay. No, just kidding. But you'll end up with lots of very hard functions, and you can't simplify them. So what will happen is that you will change the basis. I told earlier that the notation for this is base dependent. Basically, you'll end up with the matrix. There are a set of operations. The first is searching the root. So this will give you the root. So if it's a diagonal here, the roots are A, E, I. And then, what will happen is to calculate the space. In French, it's engendré par le uh, engendré par la racine. So it means that the root will have its own space. There will be a space just for this root plus a space just for this root. So each of them will be a space. So a space for a root, a space for another root, and a space for a third root. So you'll have a 3D dimension for a 3D matrix. So you'll calculate the space that in French it's kind of philosophic because it's the space in which the root gives birth, because it's weird in French, but the space where the root alpha gives birth, it's actually vect of the x minus x b, because of the matrix B, and it's the space of B engendered by the root alpha minus alpha identity of the exponent n, of the order n, sorry. So each of these will solve the equation so that you'll rebuild the matrix, rebuild how it works with this, but with different terms. Okay, so yeah, so you have this, and so as I said earlier, you'll end up with the determinant of, can I copy paste this? Of what, for fuck's sake? You'll end up with the determinant, wait, not determinant, wait, let me see, determinant, it's vect. Vect means that it's the space engendered by it, so it means that all lambda, for lambda in reals, so it's vect of this matrix, but minus alpha minus alpha minus alpha. So usually you'll solve this pretty easily because you'll end up in the system. You'll end up with the system. Can I write this, please? Can I write this, please? Can I write this, please? Yes, I can. So you'll end up with I set x, y, and z as being variables, like a Pokemon. Uh, what's happening? Okay, I minus alpha. Why is it lagging? Please, it's Word, dude. Okay, please stop. My computer is freezing. X1. Well, no. Fuck, it's fucking freezing, dude. It's fucking equation. It's just a fucking equation. Can I fucking write my equation? Oh, I think it crashed. No, it didn't. Okay. No, I'm going to name it x plus b plus b y plus c z equals 0. Then what? Okay, I had Fernum off for some reason. Please 0. I want to write. Okay, 0. Dx plus e minus alpha y plus f z equals 0. Fuck. Gx plus hi y. Yeah, word is lagging. It's a very tough problem, and also Heidecon. Z equals 0. Fuck, I can't write 0. Okay, so you'll solve this. So as I said earlier, there is, for this system in general, there is only either one solution for a 3 by 3, sorry. There is only one solution or infinite solution or no solution. But since it's a root, by definition of itself, with very strong mathematic resources, it's actually sure that you'll end up with a solution for this. There is a solution at least. There can be 2 or 3, but I'm not going to talk about it. I just consider the case where there is only one, which is what mostly happens. So you'll solve this, and you'll end up something like x equal lambda y y equals z, and x equals lambda z. Okay, once you find this, what do? You have this, you are pretty much fucked if you don't know what to do. You take, trivially, x equal 1. Yeah, so what will happen is actually you are giving one of the vector that solves this. So you can take any you want. You can take one, x equal 1, x equal 2, x equal 1 million, who cares. So you take x equal 1, so that gives you the vector of 3 dimensions. 3 dimensions, where is my 3D script? Hello, 3 dimensions, okay, 3 dimensions. That gives us this, so 1, lambda. So now you have the space. Well, you know that every space engendered by the root alpha that I wrote earlier, the root alpha of the matrix B on the usual base, will be written 1 1 lambda times something mu or whatever, a constant, and all of this will be one of the space. You repeat the operation, so you'll have the second space and the first space. So you'll end up with 3 roots, 3 things like this. And what will happen is actually that you can rewrite B, the matrix from the beginning, this one. You can rewrite it as being P times delta, oh shit, I can't write delta times P to the power minus 1. Okay, so once you have this, once you have this, you have 2 very important things. First, you can notice that there is a p and a p minus 1. This is the formula of the change of the basis. So, but basically what you have is that you have your delta that you switch from base, and this is one of the most useful writing for matrices, because you'll end up with a thingy like this. And for it's very used in statistics, in quantum mechanics, in mathematics, anything that implies convergence, because actually you can write p to the power n equals p delta p to the power minus 1, power -1, times p times delta times p to the minus 1, and I think you got it, because this will simplify into nothing. So you'll end up this, and this is delta to the power 2. And since you are iterating this process n times, you have this. This is used for convergence, because when you have a matrix in statistics with like thingies, weird stuff like this, you don't know what to do. So what you'll do first is, first you'll transform into the polynomial, then you'll solve the polynomial, then once you have the roots, you calculate the space, each of the space of the roots, then you calculate, you calculate it, so you have e to the alpha of the matrix B equals mu, well, technically no, vect, sorry, vect. And you end up this with P. P is actually the apposition of each of the matrices. So for example, sorry, I didn't told what delta is, sorry. Delta equals, oh no, wrong script. Delta, no, not like this one, is a diagonal matrix with all the roots, so alpha, beta, foc, gamma, and all the rest are zeros. So it's a matrix like that. And the order actually matters, because the P will be, I'm going to copy paste this. P will be for this column, for this P, sorry, P equals the vectorial space, the subvectorial space for the root alpha. So as I wrote, 1 lambda lambda lambda, but you can actually swap the roots. So if you put beta here and alpha here, you'll have to swap the space at which it gave birth. The E alpha, if you swap to beta, so you can just swap the order of it in the matrix P. So P is dependent on delta, and yeah, you'll get this, b to the power n equals p delta to the power n p minus 1, which is a very, very interesting result for all mathematics. I'm going to give a theorem that is very useful, is that all polynomials have a root in complex plane, that I'm not going to demonstrate it, but you know that every polynomial of order 3, so no, sorry, order, well, with something like you can write x to the power 3 plus x to the power 2, well, with ABC as thing here, ABC plus my dick, plus things, equal, you can equal 0, admits one real solution. This is actually given by one of the strongest theorems that exist in terms of mathematics. So basically, it says that if you, since there is three, since there is there are three solutions for this, you have either the case that it's all complex, or that there is one real, well, admits as at least one there is two cases. Either it's all complex, either there is one real and all other complex, either two are real or two are reals, and one is complex, or all are real. So, sorry, either you have something for everything that for roots that are all real. It means that the curve will, you have your zero axis, and then it means that it cuts 1, cuts 2, cut 3 on the complex plane. Shit, how am I going to demonstrate it? On the complex plane, there is a function that touches the 0. So, okay, I'm going to do something here. Yeah. So, complex plane, trivial, complex plane. This is 0, so it means that oh shit, I can't represent it. Okay, I can't represent it, but it's a property that you must know. Yeah, what to say? Shit. Oh yeah, shit, I can't do that. Right. I think that's pretty much all for polynomial. Thanks for watching YouTube. Drop blue thumbs, and bye. See you next time.